So let's get started with the atomic structure and periodic table review. This is the part one of my Regents Chemistry review for this year. What I did is I took the last three June Regents tests. I think the June Regents tests are different tests as opposed to the January and August. I took the last three June Regents tests and I cut out basically all the parts of the test that are not atomic structure and periodic table for the most part. And as you'll see, the test goes in a particular order, so you can actually identify what part of the test you're under. But using the last three tests and cutting out all the other parts of the test that aren't part of atomic structure and periodic table, there are some serious patterns that you could observe and learn from in these tests that the concepts repeat over and over and over. The best way to utilize, I think, this resource is to take my resource in the description, take the blank resource to PDF and do this and then come back to the video. Or you can just do what you want and just stay on for the ride. Any case, here we go. Let's be crazy and start in order with number one. And again, I'm not going to go over which test. You can see the tests that I do, but you can see how these repeat. So number one of last year's test, which description of the atom is based on the results of the gold foil experiment in the early 1900s. This is an experiment that comes up over and over and over again. You have to know that the gold foil experiment had basically two conclusions, because when they shot alpha particles, which you should know are helium nuclei, 2 protons and 2 neutrons at a very thin gold foil, most of these particles from alpha radiation went right through this very thin gold foil. All right, so you see that this gold foil is about an atom thick. It's probably a few atoms thick. They can hammer it out, and when they shot these alpha particles from a radioactive decaying metal, the detector, the scintillating screen, lit up when the alpha particle hit it to show that the particles went right through. So because most of these rays went undeflected, or I should say alpha particles went undeflected, that meant that most of the atom is empty space, and that the entire mass of the atom is found in this very small nucleus. So what the discovery that came from the gold foil experiment was that they discovered that the nucleus was a small part of the overall atom. There's the empty space part, and that all the mass was located in that small space. We should know that neutrons and protons have that mass, whereas electrons are in that space outside that nucleus, and although they have some mass, their mass is about 2,000 times lighter than that of a neutron or a proton, so they have insignificant mass. Any case, they have a small, dense, positively charged nuclei. And you say, where do we come up with the positively charged part? Well, we know that an alpha particle, being 2 protons and 2 neutrons, is +2. If you go to table O, I say that because that's just how you remember it. You look up table O, you'll see that you'll have a mass of 4, and you'll see that number 2 above, that's the charge number in the nuclear equation that's given for alpha particles. So it's +2. And being +2 would mean that it's going to deflect away from other things that are positive, and that's why there's some deflections, because the particle's positive, therefore the nucleus must be. So in any case, very big concept number one is 3. You're going to see this over and over as we go to different tests, and you're going to see my explanations get shorter as I go over the same types of questions as we go through this. So on to number 2 of this multiple choice of last year's test. According to the electron cloud model, stop. The electron cloud model is the current model of the atom. You had a bunch of models that you discovered, or at least learned through the process of your year. And the electron cloud model is the current model. It's also called the wave mechanical model. All right, it's based on the idea, and this is very important that you know this because it's coming up. There's some catchphrases. It's based on the idea that electrons have wave and particle behavior. All right, it's the duality of nature, that electrons aren't just these solid little particles at a -1, they're also waves. Tough to kind of grasp, and so quantum mechanics, which this is a part of, is not an easy topic, but you just got to know the catchphrases. They have wave and particle behavior. They can both be a particle and a wave, and they exist in regions of space called orbitals. And their behavior is based upon probabilities. Because they are waves and particles, you don't know how many we have and what they're doing exactly. We can only look at a group of them using probabilities. Those are the catchphrases that you need to know when you hear electron cloud model or wave mechanical model. And I drew a description right here. This would look like the nucleus would be here, and these dots are the possibilities, right? The probabilities of finding an electron there. So the biggest thing is, in this question, where's the most probable location? Notice the word probable, okay? Again, where are we going to have the highest probability? That's what that's talking about there. The most probable is the highest probability, okay? So again, probability, place where they exist as orbitals, and they have wave and particle behavior. So in this question, they were looking where are they located, and the location that these particles exist in are orbitals. All right, and I believe that is due to the next step in the model. It came from the Bohr model, who had electrons traveling in these orbits like planets around a sun. So the next step was to call them orbitals. Okay, all right. So number 3, and if you notice, the first 2 questions were about atomic structure, and we're still in atomic structure. That's how these tests work. So in number 3, we're still there. You can expect the first 5 or 6 questions to be atomic structure, periodic table. So here we go, number 3, which change occurs when an electron returns from a high energy state to a lower energy state? You have to get this down. We're going from a high energy state to a low energy state. The only way to get to a low energy state is to release the high energy you had. So this idea that you're going to absorb or emit, you got to figure out that we're going to emit energy. That's important. So 1 and 4 are your only choices. If you're going to move from a low state to a high state, you have to gain energy. You have to absorb it to get to a higher position. That is a big concept in this course. Any case, now, so again, which question? An ionic compound is formed, energy is emitted. We're not talking about energy states of electrons. We're talking about the position of electron in a particular orbital or shell. So if we look here, I've got a little model here. Here's my nucleus here that's positive. And then we're in the first shell. You should know the first shell, or the first orbit, or the first orbitals, I should say. And again, I'm kind of using the idea of orbits for my analogy here, but the bottom line is electrons are in positions based upon proximity to the nucleus. How far away are they? So if you're in the first shell, that would be orbitals that are closer to the nucleus. It'd be 1 orbital actually, but so if we're talking about the first shell, the first position where electrons exist, hey, they get closer to the nucleus. They feel the nucleus the greatest. So their attraction would be the greatest. And because they feel that attraction, they'd have lower energy. Things that are low energy are stable. These are important concepts you need to have down. Even though this question may not be exactly talking about these exact concepts here, you will see other questions. So I'm teaching the concept behind the question. Now, we're going to go from a high energy state to a low energy state in this problem. We have to admit it. Well, that would mean that an electron is moving farther away from, or excuse me, is starting farther away and moving closer. Because when you're farther away, you feel the nucleus less. Because your distance is so far away, it's hard to feel that nucleus. Therefore, you're not controlled by that positive charge. Don't forget, negatives and positives attract. The farther you are away from that positive, the less there is an attraction. And that means that electron is not going to feel that positive energy and is going to have higher energy. And you should know electrons that exist farther away are called excited. Okay, they're in an excited state. And electrons that are in their lowest energy, the closest to the nucleus, they're in their ground state. I should put that here, and I am. Ground state, closer, feel the nucleus, you're stable, electrons don't have much energy. If you're farther away from the nucleus, you have higher energy and excited. So what they're describing is an electron jumping back toward the nucleus. And in the process, going from high energy to low, guess what has to happen? Energy has to be emitted. And you should be aware that this energy is in the form of light. We'll call it spectra. And that spectra, or that light energy, is very specific. The atom is quantized. For electrons to go to different energy levels, we say that they have to move in specific energy increments, not general. So there's an exact amount of energy that has to be lost for it to get to the second shell moving to the 1, or if you go in reverse, the energy that had to be absorbed to go from 1 to 2. So this is important. So back to the question, a specific amount of energy is absorbed. This is called quanta. Quanta is part of the current model of the atom, where electrons absorb or emit specific energy levels to get to different distances or shells from the nucleus. So in any case, 3 is 4. On to number 4. Which phase describes the different isotopes? They love isotopes. The word iso means same. And what's a great example of an isotope? Carbon-12, carbon-14. They are the same element, same what? Proton number, and they have a different number of neutrons. To remember to get your proton number, it's just the atomic number on the bottom. It's also the electron number if it's a neutral atom. Atoms are always neutral. And the top number is the mass number. And since protons and neutrons have the same mass, hey, all you have to do to get neutrons is you subtract the bottom number from the top. So 14 minus 6 gives you 8 neutrons for carbon-14. And carbon-12 has 6 minus 6 from 12 is 6 neutrons. These are isotopes. They are the same element, same symbol, same atomic number, same protons, but a different number of neutrons, therefore a different mass number. Okay, you've got to have that down. So essentially I just said that same number of protons, but different number of neutrons. And by the way, we're going to see these same types of concepts right in the free response. People are afraid of the free response. Oh, you're working on the multiple choice, what are the free response? It's the same concepts. They just dress up the problem a different way. And I'll give you an example of that. All right, so 4 is definitely 3. Pretty much word for word definition question. Is there a number 5? Yes, there is. A 5 and 6 here. Okay, so number 5. Although this might not be atomic structure, but this is kind of filtering in, we'll do chemical property. It's in this area. Which statement describes a chemical property? Right away, a chemical property is the ability of sodium to exchange electrons or share electrons, it'd be exchange, but with other atoms to make a bond, to make a compound, to chemically react. Chemically react means you're going to build a different formula. So if you look at your choices, silver is not a chemical change, or a color of silver is not a chemical change, because we can identify this property without reacting it or changing it. Remember, chemical changes means that there's going to be a new formula, a new set of properties resulting from a chemical reaction when you make a new substance that has new properties by breaking or making bonds. Identifying something's color doesn't do that, so it's a physical. The density of something is also a physical property, because we're not what? We're not seeing something change to do that. To measure something's density, like aluminum, we measure its height, its width, its length, and then we get its volume, and then we use its mass and use the density formula to get the density. But that's not changing anything of aluminum. So that's also going to be physical. And then 3, knowing its atomic radius, or measuring its distance of its atomic radius from its nucleus to the outermost electrons, is also a physical property. We're not changing anything. But when we say it's highly reactive with water, well, then it's going to make or break new bonds. It's going to make some new bonds and create a new compound. To react with something means you're going to interact in a way to either break bonds or make bonds, but the bottom line is you're going to make a new substance. So reacting with water is going to create a a gas or a new compound. So the word reactive is kind of in there as well. So number 4 is your answer. Number 6, ozone can exist as a diatomic gas. Okay, these two forms of oxygen. Notice they have two forms of oxygen here. We have O2 and we have O3. They're both oxygen because oxygen is the word that describes the element. The word element is a group of the same type of atoms. So O2, 2 oxygen atoms, O3, 3 oxygen atoms are still what? A group of the same atoms. So they're both oxygens, but they're going to have different properties. Why? Because they must have different structures. I will say this over and over again, especially in organic chemistry. Structure is king. You change the structure, you change the physical and chemical properties of things. So structure. By the way, you also have a fancy word for these, allotropes. The word allotrope is a different structure for the same element. For instance, the greatest example is carbon. Carbon is made of, we just talked about, an atom with 6 protons. But if it forms a unique structure to make graphite, pure carbon can be graphite, which is essentially the compound that you, or the element you write with. And then diamond is also made of pure carbon. How could pure carbon be something that's the tip of your pencil or be something that you can wear in jewelry? Clearly, diamond and graphite are very different because they have different structure. They're the same element, but different structure. Different structure, different properties. You will see this over and over and over again. All right, so that concludes the first 6 questions of this test, but also you should recognize that the test goes in order, generally speaking, from atomic structure all the way through to the nuclear chemistry to question 30, generally, okay? And then it starts over at question 31. Okay, and it'll go from atomic structure again, and 31 through 50 are supposedly a little more 2-step problems or application problems where you probably have to go to a reference table or make a calculation. So let's go to the first few questions of this test to show that we're still going to be in the atomic structure and periodic table area. All right, so 31 of the first test I'm going over, which is 2024, gives me this atomic structure question, where they give me a chart and they say which ion has the greatest mass. And for the ion, they're giving me a number of protons and a number of neutrons. Now, if you're totally lost here, we have a table here. And in the table, I have let you know what electrons are. And by the way, if you didn't know, beta particles are electrons. Then we have the neutrons and the protons. So all the subatomic particles' masses are listed in table O. I rewrote those over here underneath table O. And even though they don't write it, you should know that beta particle is an electron, and they put a mass here of 0 to remind everyone that electrons have an insignificant mass to the overall atom. But truthfully, they do have a little bit of the mass. But the mass of these ions has nothing to do with the electrons. So we don't have to consider electrons here. And the reasoning is because electrons have insignificant mass. If you forget that, table O finds that. So if we look at table O, there's a mass of 1 for a neutron and a proton. So what's this tell us? This tells us that all we got to do is add up neutrons and protons, which is the atomic mass of an atom anyway, in this case an ion. So all we have to do is add them up. And so I did that. So a little plus sign, all right, in the middle here, I added these up. And I got a total of 120, 50 plus 70, highest number, and that is going to be ion E, choice 2. Very simple. If you didn't know these particulars because you're reviewing with me, now you do, but table O is your friend. People teach table O for nuclear chemistry, but what's in the nucleus? Protons and neutrons. So actually all the subatomic particles that we need for the atom are listed here to help you remind you those masses. So on to 32, which is the second part of this test. And you can see we needed a little bit more information for this kind of question. That's why they deem this the part B1 of all things. Okay, so on to 32. The mass of a sample of nickel is determined to be 20.40 grams. How many significant figures are used to express this mass? Okay, so this question is from like out of left field. It's not fitting anywhere in a periodic table or atomic structure, but I'm going to do it anyway. And a couple of things you should recognize for 20.4, I wrote this over here. The answer is 4 significant figures. What's a significant figure? All numbers, including the guess, that come from a measurement device. That's a significant figure. So all the numbers that come from them. Remember, there's going to be numbers that we get from actual numbers, and then lines in between numbers. Those, of course, are called calibrations, but they represent a number. And then there's a guess, the last little value in between your last calibration. So which of the following numbers came from a measurement device? Well, very simple. You have basically 3 rules. All non-zero numbers are significant. So we know that this 2 and 4 are non-zero. They're significant. So we got 2 so far. Zeros in between numbers are significant. So that gives me 3. And ending zeros are significant if a decimal point is present, because ending zeros can become what we call a placeholder, and placeholders don't ever count. But in this case, I have a decimal point here. So ending zeros count, so this would be 4. All right. Any case, moving on to 33. Again, and not quite in the area, but we'll do it anyway, of atomic structure, but the naming part kind of fits in this way. So what's the chemical name for the compound lead O2? Yeah, well, the first thing I had to recognize is, what is this Roman numeral thing? It's called the stock system, and it's for the positive charge of the first element. So if I know it's PbO2, and I know from the reference table, oxygen loves to become -2. So if you look at the oxygen in your reference table, the upper right hand corner, you'll see -2. It loves to become -2. Now there's 2 of them, my friends, in chemistry. So 2 times -2 gives me -4. The whole thing has to equal 0 because there's no charge written. So the lead has to be +4 collectively. Because there's only 1 lead, hey, it's +4. Now if you do look at the periodic table, as I said, for oxygen, upper right hand corner, it's -2, but for lead, they're going to post +2 and +4. Lead can be 2 different positive choices. In this case, it has to be the +4 charge. So therefore, we have to write the Roman numeral 4 in front of the oxide. This is a binary compound. When you name a binary compound, it ends in IDE. So we needed a +4 there. And we had to figure out the oxidation state by what I just did here to do that. By the way, PbO would be lead 2 oxide, because if this is -2, this lead would be +2 in this case, and this would be the answer. So it's the Roman numeral is the actual charge of the leading element's positive charge. And we use it when those leading elements that are positive have multiple charges. We had to figure that one out. Okay, and then 34. Which formula is the empirical formula? Empirical formulas are the lowest ratio. Get that down. They're lowest ratio. We find them in laboratory. And the things that are lowest ratio are salts, but things that are molecules, things that are made up of nonmetals and nonmetals, they exist in molecular formulas. But in any case, they want the lowest ratio of C2H6. Just reduce it. 2 to 6 becomes 1 to 3. So that's why 2 is the answer. 34 is the lowest ratio. Simple as that. All right, and I think that's all the questions I got. All right, so keeping on this momentum, let's go to June 23 and see how these types of questions do repeat. So on to number 1. Which phrase describes the nucleus of an atom? Well, based on what we just did, the nucleus of the atom is that small, dense, positive charged area that has the protons and neutrons mass. So has an overall positive charge. It's where the protons exist. The neutrons exist there too, right? That's the thing about the gold foil experiment. We discovered that the entire mass of the atom was in that small spot, and it's positive. Why is it positive? If you forgot the first one, let's go scroll back. What was the answer of the last test? Atoms have a small, dense, positively charged nuclei. Well, let's look at this test right here. It's the same question dressed up differently. Which phrase describes the nucleus of an atom? Has an overall positive charge because of those protons with the neutrons in that very small part of the nucleus. As you can see, a lot of repetitiveness here. Okay, but that's the point. That's the point. Pick up the patterns. Two, which two particles have a mass of approximately 1 mass unit? Boy, that sounds familiar, doesn't it? Table O shows us a mass of 1 for neutrons and protons. Come on, party people. So clearly it's neutrons and protons. Okay. Again, I said I would pick up the pace here because we're seeing the same what? We're seeing the same or very similar concepts. Now, if you forget that protons and neutrons are the same, table O is your friend. On to number 3. The wave mechanical model. Boy, we've heard about this. Now, they called it in the last test the electron cloud model, but I remembered I told you the electron cloud model is also the wave mechanical model. Get those words down. Again, it's still the current model of the atom, and they want the location of electrons. My gosh, what are the catchphrases? It's based on probability. Electrons can be waves and particles, and where they exist is in orbitals, just like the last test. Okay, and again, if you want to do a quick comparison in the first 3 questions, okay, where are electrons found? And they said the electron cloud model, but that's still the wave mechanical. Notice the answer here is orbital. Okay, just like the question we just did. Lot of what? Reproducibility here. They're just going to dress up the question. That's why you've got to understand concepts. Okay, any case, on to 4. When a ground state electron, whoa, what's ground state? Look at my drawing over here. Ground state means like you're grounded, you're close to home, you can't do anything. You're close to what? You're close to the nucleus. That means you're being attracted really, really strongly by those positives. You can't move much, you have lower energy. Therefore, you're very, what? Stable. You're grounded. Now, if it moves to an excited state, what happened? Well, excited state means you have higher energy because these electrons can exist farther away from the positive because they have the energy to pull away. And therefore, they have higher energy. So we're going to go from a low energy state that's closer to the nucleus to a higher energy state. This is the opposite of what we just had in the previous test. So you're going to have to absorb energy to pull away from those positives to move to a higher energy state. You have to know for this test, even in the FRQ position, electrons that exist in shells or orbitals farther away from the nucleus, those electrons have higher energy. They don't feel the what? Positive pulling force that much. Electrons that are closer, okay, are felt very strongly by the nucleus. They don't have the what? Same energy because they're being controlled. All right, so we're going to a higher energy state. We're going to need energy. And by the way, the energy that gets absorbed can be a photon of light. All right, any case. And that same amount of light is what gets emitted when it jumps back. Very important. All right, any case, on to number 5. Oh, chemical property of iron. Oh, I think we've seen this before. Yeah, so a chemical property, again, is a property that describes how a certain compound, or in this case, element, how it will change into a compound, how it will react and make new bonds with other atoms. And when it does that, it makes new properties. Okay, the properties are changing. Now let's look at what's a physical. Well, iron is malleable. Malleability is the ability to basically hammer it into different shapes. Well, iron can be done. And iron hammering it into a different shape is not a chemical change. We're not changing it, we're just changing its shape. So that's physical. Its ability to conduct electricity is a physical property based upon its electrons and how loosely they're held and how these charges can move. To conduct electricity, you have to have free moving charges. So this would be a part of metallic bonding. But you're not changing iron by measuring how well its electrons move through the same substance. If I go on to 4, has a high melting point. Don't forget that melting points, boiling points, condensation points, anything that's a phase change, you're not changing the what? Chemical formula. Iron solid, going to iron liquid. Okay, that's melting. Solid is melting to a liquid, but it's still iron. We're not changing anything. That's a physical change. So phase changes are physical changes. So the temperature the phase change occurs, it still would be a physical change. But in number 3, iron reacts with nitric acid. It's using the word reacts. It's making bonds, making something new. All right, so very similar questions here. All right, so on to some other things. Number 6, look at this. Diamond and graphite. I thought I might have mentioned these. Are two forms of solid carbon. Whoa, they're both made of pure carbon, yet we know diamonds and graphite have very different properties. Who is king? Structure is king. Very similar. Different structures, different properties. It's as simple as that. And they can ask for that in the FRQ. Describe why diamond and graphite have different properties. And you just say different structures, different properties. Okay, structure is king. These are allotropes. So you can see how this question, very similar to what we've already handled. And this is the repetitiveness. This is what you want to get to when you're studying. Oh, I've seen this before. Oh, this is just like the other questions. Yeah, because you get your understanding concepts. Number 7. Which subs can be broken down by a chemical change? I included this one because, well, chemical changes are breaking bonds or forming new bonds, or these are chemical reactions. And if you look at your choices, choice 1, 3, and 4 are all elements. You can't break an element down into anything simpler. It's basically the simplest form of matter we have in this course. So how do I know these are elements? I can go to table S, the most underutilized table in the reference tables you have. People forget to use it, and you could look up these elements and see that they're elements. Ethane, you should be recognized from your organic unit. Eth means 2 carbons in table P. And ane means a single bond in table O. And there's your compound. All right, and now how do I know that that's a compound? Well, because I know it's 2 or more different atoms bonded together. And they can be broken down because they're bonds keeping multiple atoms together. That was key. We're looking for a compound there. Very simple. All right. All right, so let's go on to the next test. That was June 2023. Let's go to let's go to June 2023 at the question 31 as we start again. So the second part again. Okay. So number 31. Now we're starting the test over again. We're in atomic structure, and now they want us to do a Lewis dot diagram of an element. Very simple. The dots that you have to draw for the element are the valence electrons. These are the electrons that are in the outermost shell. The arrangement of electrons in nitrogen. Notice atomic number 7. That's the proton number. That's also the what? The electron number, because positive 7 with a negative 7 gives you 0. Atoms are always neutral. And what's the arrangement? Well, that's what this is, 2-5. There's 2 electrons in the first shell close to the nucleus, and then there's 5 electrons in the outer shell farther away, higher energy. And those electrons that have higher energy that are farther away are called valence electrons. So what's the outermost number of electrons you have? 5. Then you must draw 5 dots. It's that simple. So we just need 5 dots for the 5 outermost electrons. Nothing you have to really know other than the dots are the valence electrons, which should make sense because when you do dot diagrams, you're starting to show how things bond. And we always bond with the high energy electrons, not with the electrons that are close to the nucleus that are called kernel, that are stable. Only the unstable electrons are involved, the outermost, the valence, in bonding. Okay, 32. Oh my gosh, we got the word isotopes again. And this, my friends, is the weighted mass problem. Classic one. Okay, and you'll see this in part 2 a lot, where what they have is they have 2 isotopes. Notice there's silver. They're giving me a mass number. That mass number, of course, is indicative of the fact they're different because of different neutrons. They have the same proton number, silver, same symbol, same proton number, but there's a difference of 2 neutrons here. Now, when they actually go get the actual mass of these, they have some decimal places, and this is the natural abundance in nature. So when we do an average to get what we call the atomic mass of silver, we're considering all the isotopes that exist for silver, but we also have to consider their relative abundances of nature. We can't do a straight average. So all we're going to do here is do the weighted mass problem. And all we're going to do, okay, is find the percentage, 51.8% of this mass, and then add it to 48.2% of this mass. Now, when I saw this question first given, I didn't like how they gave it out because they have the percentages there. So I think that was kind of misleading. When you find a percentage normally, like if I want to buy a dress and I know it's 51% off, how much money I'm going to save? I'll take the percentage. I'm going to move the decimal place 2 places over. And then I'm going to times it by that. You notice that there was no choices that were 0.58 times 106.9. And then you're going to add it to what? 0.482 times 108.905 either. There was no choices there. All right, so the other choice that could only be right is they have the percentages written. Percent means that it's this number divided by 100. So I did not like this. The first time I've seen this, maybe it's some other place that I haven't seen before, but it's the only choice that makes any sense, and I thought that was a little bit misleading. Most of the time, they'd give you a choice like this. Okay, you're moving the decimal place over to the left, and then you're going to add it, multiply that by the actual atomic mass, and then you're going to add that to the same, well, a different product of the abundance and atomic mass together, as I showed here. So the only correct answer is B. So, number 2. Again, a weird way to do that problem, but again, I see this question all the time in your free response. You can expect this question. Make sure you understand it. Number 33. The mass number is 37. What's the number of neutrons? A straight atomic structure question. We talked about this skill. The mass number is on top. The mass, or the number of protons, is in the bottom. Since the entire mass of the atom is protons and neutrons from table O, 37 minus 19 is 18 neutrons. Very simple. Okay. 34. They want you to do a percent error problem. And again, this is not particularly part of atomic structure or periodic table, but it is a property, a physical property of density, and it definitely has some work here, but they want you to find a percent error. They said the student determines the density of the sample to be 9.76. So the student found this. This is the measured value of the student. Okay, so that's what this value is here. We need the accepted value for nickel. Where did we look? Oh, they told us table S, so we found that, which is 8.90. I kind of rewrote this right down here. Plug that in here. And then you divide by the accepted value times by 100, you get 10%. So pretty straightforward. If you didn't know what percent error formula was, you forget it, like my students. Number 35 is our periodic table question here. Finally get some of these. In the next couple of tests, we'll definitely hit more of these. But compare the metals in period 2, that's row 2, or principal energy level 2, or N equals 2. Those are important synonyms there. Non-metals in period 2 have what? Well, you have to understand, if I'm in period 2, my friends, in chemistry, I have this cutout of your reference table. You should know your non-metals are above the staircase. Boron is a metalloid, so you should recognize that these are your non-metals here. And it really doesn't matter, but the nonmetals, of course, are going to be those elements that have a higher electronegativity, because compared to the metals, they have a greater number of protons. So electronegativity, we see the word electronegativity and ionization energy. Electronegativity is the easy one to know. That's another word, another important synonym that describes the attraction for electrons simply. The best answer, or the best description of electronegativity, is attraction for other elements, electrons in a bond, but we'll take attraction for electrons for sure. And the best way to think about this is that the protons are in the nucleus, they're positive, and the greater the nuclear charge, since the only thing in the nucleus, remember it's atomic structure too, the only thing in the nucleus is protons, which are positive, and neutrons, which are neutral. So the number of protons determines the size of the positive charge. And since the atomic number, my friends, in chemistry is going up as we go across the period or the row, the more protons you have in the same row, in the same energy level, okay, in the same period, the greater the attractions that the electrons have. You may say, well, I'm adding an electron every single proton I add. It doesn't matter. Electrons almost have no mass. Protons have a mass and equal and opposite charge. So the electrons actually will move in a little bit as you add more protons. If we think about electrons as a small car and the protons as a large, heavy truck, we can clearly see if they both have the same pulling force, which is false, a little small car will not have the same pulling force as a heavier truck. Let's pretend that they do have the same pulling force, and that's the analogy for the positive attracting a negative. Who's going to move? Is the heavy car going to move or the lighter car going to move? Well, the lighter cars are going to move. So as you add more protons, even though you're adding more electrons, which are insignificantly light, they're going to be pulled in. You're going to attract electrons more with a greater positive charge. So the electronegativities, okay, are going to be greater. So look at the question. Compared to metals, that's the elements off to the side. These are bigger atoms. Non-metals are going to have a higher attraction, a higher electronegativity. Say it to yourself. Electronegativity is attraction. Okay, so 4 and 2 have that. Now, what's ionization energy? Ionization energy is the energy needed to pull electrons away from a nucleus completely. And if you think about it, the greater number of protons, which would be the greater the nuclear force or the greater the positive force in the nucleus, the harder it will be to pull the electrons away. So those elements that have the greater number of what? Protons or a higher nuclear charge also will have a higher ionization energy. It'll take more energy to pull them away. And if you don't like any of that, and it's good to know your trends that way, you've got your most underutilized table, and that's table S. And if you compare a metal like lithium, which is 520, and compare it to, let's say, nitrogen, or in this case carbon, it's 1086, you can see that the nonmetals, like carbon, atomic number 6, has a greater first ionization energy. And you do the same with electronegativity. So you could just look at table S, most underutilized table here. Okay, so the beginning part I explained in terms of the trends, but table S is your friend there. Okay, so in any case, on to 35 is 4. So now I'm going to go a little quicker. The last test that I have here, I don't want to keep you too long, but I want to go to the last test here and show you how much of these questions are starting to repeat. If you stayed with me, stayed through this, good for you. Okay, the reward is that you're going to see these patterns. And once you see these patterns, you're understanding these concepts. Okay, number 1, this of course is going to be June 2022. I did these consecutively. Okay, so number 1, which subatomic particles are matched with their charges? Well, of course, protons are positive and electrons are negative. They're also opposite and equal in magnitude. They're both have a charge of 1, one being positive, 1 a negative 1. Sometimes you hear that. So 1 is equally 2. Oh my gosh, 2, they're asking about the gold foil. Which conclusion directly resulted from the gold foil? Atoms are mostly empty space. Oh, that's one of the conclusions. The other one is that the nucleus is dense, small, and positive. All right, so that's very straightforward. Number 3, the bright line spectrum. Now, we haven't talked about this, but we did talk about the idea that spectra, or light of a specific energy, which would mean a specific color, is given off when we jump backwards. Right? So this leap right here is of a particular distance that has an exact energy. So what's bright line is an exact color is giving off in a spectroscope that's indicative of a certain wavelength and a certain color of a certain energy that's indicative of an exact leap. We can use bright line spectrum, of course, to identify individual elements, because different elements have different number of electrons, different number of protons, and different energy levels in their leaps. But it must leap back from higher energy farther away to lower. So if we're going to give off energy in the form of light, and is when the excited state, these are the electrons that are farther away, higher energy, feel the nucleus less, jump to a lower energy and become stable. How do they get lower? They give off energy in the form of light. That's the spectra. That's the bright line. That's the color. So they release energy and move to lower energy states. So this was the same question, just introducing a little more detail to the concept. On to 4. Elements on the periodic table are arranged in quarter of their atomic number, not their atomic mass. There's going to be places on the originally the elements were first by Dmitri Mendeleev put together by atomic mass because there was no atomic number in the 1850s or 1860s. They just knew the atomic masses. But that was later rearranged a little bit when Moseley found that every unique element has a unique number of protons, and we put them in order of the protons. So it was rearranged a little bit, but everything goes in order of protons, which, by the way, is the atomic number. All right. Number 5, which atoms in group 15 have the greatest electronegativity? Well, this sounds what? This sounds familiar. Electronegativity is attraction for electrons. And who's going to attract them more? Well, the ones that are smaller atoms that are able to pull their electrons in. So as you know, when you go down, and this is a periodic question, a periodic trend question, as you go down the column, the atomic radius gets bigger. That means there's more shells, okay, as you go down. And that means that electrons are farther away, and that means they're not attracted as much. Even though you have more protons, bismuth has 83 protons, nitrogen has 7, but because they're so far physically away, those outermost electrons, they're not attracted to the nucleus that much. And so you should know that electronegativity, the attraction for electrons, decreases as the atom gets bigger. Okay, we go across the row 2 here, the atoms get smaller as we add more protons because we pull in those electrons. Higher electronegativity with smaller atoms. But if you don't like any of that, you can go to table S and see which one is going to have the highest electronegativity, right? You can just look it up and compare. There's no reason to get this wrong, but you should understand the trends. So that's why choice 3 is the answer there. And that's, one more here for number 6. Simplest whole number ratio. Well, we've seen this before. That's called an empirical formula. And the other questions that we've done, if you stayed with me through this, hopefully, the empirical formula was the lowest ratio. You needed to know what this was. So they just kind of flipped the question and said, which one is the simplest whole number ratio? All right. Now let's go on to the 31 through 35-ish. These questions are atomic structure. Here we go. Which configuration represents the electrons of phosphorus in the excited state? Excited state means electrons jumped farther away from their ground state. And notice they're looking for a phosphorus atom, which means the number of what? Electrons equals the number of protons. This is the arrangement 2-8-5. That's 2 in the first energy shell, or the period or row. 8 electrons maximally fill the second shell, and now you have 5, and that's your valence electrons, and that's ground state because we can't go to the third energy shell until we fill the second. It's called the Aufbau principle, but more importantly, electrons go in order from lowest energy to highest. So that's called a ground state. Looking for an excited state, looking for something that's going out of order but has the same number of electrons, 15. And so if I look at choice 1 and 2, there's a ground state. 2-8-5, 2-8-6, those are not going out of order. If you look at choice 3 and 4, those are excited because now we're going out of order. Instead of being 2-8-5, it's 2-7-6. Why? Because an electron jumped away. Same thing for choice 4. They're both excited, but how do I know which one's a phosphorus atom? You hear the word atom, you think neutral. Atom neutral. Protons equal electrons. I'm looking for something that equals 15. 15 is the proton number. And that's choice 3. And you can see 2-7-6 is a lot like 2-8-5. If one of these electrons from the second jump to the third because it absorbed a specific amount of energy. This would become a 7, this become a 6, and that's why choice 3 is the answer. Okay, 32. Which element has a volume of, they give you grams and they give you cubic centimeters, which you should know is centimeters cubed is a volume. This is a density question. And by the way, you have this formula in table T if you forget. And they want to know which element has a certain amount of these things. So solve for the density, which is mass over the volume, and then go to table S and look it up. And when I do so, I find it's 8.90. It tells me it's nickel. So it's kind of definitely a part 2 or a part B1 question where you definitely had to do a couple of different things. We had to recognize the fact that we needed to go to density, which is a physical property, solve for it, and then note in table S, go find that density, go identify that element. Okay, any case, 33, which element is a nonmetal and a solid at STP? Okay, another periodic table question we haven't seen before, but we can do it. First of all, they want a nonmetal. And if you look at my periodic table to the right, everything above the staircase, these are the metalloids, these green ones here. They have properties of both metals and nonmetals. That's important. So this area here, above to the right, are the nonmetals, and this area here are the metals. Those are the big atoms, and these are the small atoms. All right? These guys lose electrons. These guys gain. But the most important thing is they wanted which element is a nonmetal. So if you look at lead, that's a metal. Look at sodium, and if you don't know that Na is sodium, table S tells you the name as well as the symbol. So we're left with sulfur and nitrogen. Sulfur and nitrogen are the two that we're dealing with here. So which one is a solid? I go to table, guess what? S again. And I look at their melting points. Nitrogen has a melting point of 63 Kelvin and sulfur is 388. Think with me for a second. They want to know which one's a solid at STP. Well, standard temperature is 273 Kelvin. So that means that I need something that is a solid and hasn't melted yet. So sulfur has not melted. It's still a solid. It melts at 388 Kelvin. I'm getting this in table S. STP is 273, but nitrogen from table S is 63. Since STP is way above 273, this would have melted already. Okay? In fact, it'd be a gas at that temperature, right? Nitrogen is part of atmospheric gases, if you didn't know that. But sulfur has not melted yet if the temperature is 273 and its melting point is 388, so that is your solid. I needed to use table S. 34. Getting back to this question, because it's important because we've been dealing with empirical formulas a little bit. Empirical's lowest ratio. Molecular formula is the actual formula that molecules have. What are molecules? Molecules, my friends, are things where nonmetals, guess what? When they bond to themselves covalently, they actually make a certain particle, which is a molecule. And sometimes they're lowest ratio, sometimes they're not. For instance, if you look at choice 4, this is a formula of a certain molecule. And it's not the lowest ratio, it's the actual formula. So a molecular formula is a formula that is between nonmetals, carbons, hydrogens, and oxygens, and it can be a lowest ratio. A good example is H2O is also a molecular formula because that's the formula of water and nonmetals. But it's also the lowest ratio too. So they just wanted the actual formula. Okay. But again, the opposite side of this, I don't think it's a great question because of that. What are these right here? So all they really wanted to do here, and understand the molecular formula is the antithesis or the opposite of the lowest ratio. And because they gave me this structural formula, all I had to do was count up. So I'm very sorry if I made this longer than it had to be, but all you had to do was count up the carbons and count up the oxygens. And I've seen this question a lot confuse people. What's the molecular? Just count it up and put it all together. Okay, it's going to be whatever the formula is. And most times it won't be the lowest ratio. But again, the idea that it's a bunch of non-metals makes it molecular. Just count them up. Okay, I think that was not as my best work right there, but hey, I'm tall. All right, so in any case, that is it for the multiple choice. I hope there you can see some parallels. My next video, I'm going to do the atomic structure and periodic table for the same 3 tests, but use the find the FRQ questions, the free response questions for these same topics. And you should do that one next once that's posted, to solidify these concepts and see that the multiple choice, if you're working on multiple choice, you're really working on the same concepts, and I'll show you that in the next video. So I hope that helped. Good luck to you. Go to table T. So table S and table T, we have friends there to plug that in. All right, pretty straightforward.